Lecture 2 on elasticity. So we start with the definition of Young's modulus, which is denoted as Y, and the definition of Young's modulus is ratio of longitudinal stress by longitudinal strain. Now longitudinal stress, so if you have a wire of length capital N and radius R, and because of this deforming force mg, if a weight is hanged on this wire, then the force is F, which is equal to mg. Then we can say that force per unit area, that is mg by 4 pi r square, divided by the change in length by original length. The change in length or increase in length is small l divided by the original length capital L. So we get from the definition force into L, so this L goes up by L into A. So we can write down in terms of force, in terms of weight, mg L by pi r square L. So this is the formula for Young's modulus of the wire, and this is the definition of Young's modulus in terms of longitudinal stress by strain. Unit of Young's modulus in SI unit is Newton per meter square, and the dimension is ml-1 t-2. Now what is bulk modulus, which is denoted as sometimes K, or some books they write B? Within elastic limit, the ratio of volumetric stress by volumetric strength. So when you apply force on a normal to the surface, then if the volume changes, the change in volume, when force per unit area, that outcomes as the change in the volume, then we say it's the bulk modulus of elasticity. So how do we define it? Force per unit area is the volume stress divided by the change in volume delta V by V, the original volume. The negative sign here indicates that volume decreases if volume decreases if there is increase in the force per unit area, that is the stress. What is the unit of bulk modulus? It is Newton per meter square or Pascal. Now bulk modulus, if you consider a gas, ideal gas, and bulk modulus, value of the bulk modulus depend upon in which system the process is undergoing. It is isothermal, or is it adiabatic, or is it polytropic? So if you have isothermal where T constant, temperature constant, we write PV equal to constant. And if you do the derivative in terms of P and V, we get P dV plus V dV, V dP equal to 0. And if you arrange it, we get P is equal to minus dP by dV by V. This part is actually the bulk modulus, the definition of bulk modulus, which is actually the pressure P. So when you consider an isothermal process, ideal gas in an isothermal process, the bulk modulus itself is pressure. Similarly, for adiabatic process, we get the bulk modulus as gamma times of P, and in case of bulk modulus for polytropic process, we write Np, where N is the number of moles. Now what is compressibility? The reciprocal of bulk modulus of elasticity is called the compressibility, which is 1 by K. K is the bulk modulus. Modulus of rigidity, it is denoted as eta. Within elastic limit, the ratio of shearing stress and shearing strain is called the modulus of rigidity of a material. So shearing stress is written as F tangential, it is on the surface, tangential to the surface by area, and because of this force, what is the twist or shift in terms of angle, in terms of radian, we say shearing strain, and that is F tangential by A phi, where A is the angle of shear, is called the modulus of rigidity. Now what is Poissons ratio? It is denoted as sigma. Within elastic limit, if you apply some force, okay, and then there is a increase in length, but because of this increase in length, the radius or the diameter of this wire decreases. So sigma, or the Poissons ratio, is denoted as lateral strain by longitudinal strain. So what is longitudinal strain? Here it is denoted as alpha. It is the change in length, that is increase in length by original length. And what is lateral strain? It is the change in diameter or the radius by the original diameter. Here the diameter changes, and that is why we say the negative sign. So change in diameter, decrease in diameter is denoted as negative by the original diameter, capital D. This ratio is denoted as beta, called the lateral strain. And if you take this ratio, we get the Poissons ratio. So what we have done Young's modulus of elasticity, then we have done bulk modulus, then we have done modulus of rigidity and Poissons ratio. With these four quantities, we find out these three relations on your screen. One of the relation is Young's modulus, bulk modulus and Poissons ratio, Young's modulus, Poissons ratio and modulus of rigidity, and Young's modulus, modulus of rigidity and bulk modulus. Now we calculate the potential energy of a wire when there is a change in length under some deforming force. And the work done, or the potential energy, is denoted as half into stress into strain into volume. Or we can say half into Young's modulus into strains square into volume. So actually half into stress into strain. So how do you write it, or how do you derive it? So we know that Young's modulus is equal to stress by strain. Now Y is equal to F by A by change in length by original length. That we know. We also know that stress is defined as force per unit area, where force can be written as stress into area. So force is equal to stress into area, and we write down the definition of stress in terms of Young's modulus as Y, which is Young's modulus into change in length. So if you consider a wire of length L0 and then under some deforming force A, it changes, the length increases by X, then we set Y into X by L0, original length L0, multiplied by A. So this stress is actually Y into X by L0, and this area is taken as A. Now if I say that what amount of work to be done by the restoring force if there is further increase in this in the length, which is, let us say, a further increase in length by dx. So we write on the definition of work done, dw is equal to f dx. So what is f? We substitute the value of this f here and dx here, and then we integrate from a lower limit to upper limit. If I want to say that this is my lower limit 0 and it has extended to some value of delta L, so if you integrate, we get w is equal to you bring the Young's modulus value constant outside and area outside and length, original length being constant outside, we get x square by 2, and then put the limit delta L in the upper limit and 0 in the lower limit. We get half into y, Young's modulus, into delta L by L0, which is actually strain, but here it is square, so we write strain square, into AL0, area into original length 0, that gives you the volume. Similarly, we can also write down, if you substitute the value of y as stress by strain, then stress by strain, so if you write, then the denominator strain will cancel with this one of the strain, and we can write down w is equal to half into stress into strain. So this is the value of the work done, or the potential energy of a wire under the deforming force. So we come to the end of this lecture 2 of elasticity.